Maybe in the break there is coffee and Gipfeli ready, so if you want.
And I have to come down.
All right then. Okay, so thank you all for coming. Let's start then. I think, yeah, the recording has started, so that should be fine. Yeah, today I'd like to take you on a small journey, taking a little bit of a step back, or a rather big step back actually, and look at our context in the history of computing, and also the history, especially of human-computer interface development. And I would say actually the invention of much of what we use today. So I like to look at history as kind of these three branches that fork from each other and sometimes merge again. And when we go to the very early history of computing here on the left side, the person I would say it starts with is Charles Babbage. He, back in the 19th century, invented mechanical computing, including like RAM and arithmetic units and storage, programmable mechanical computing. You can actually build everything that we know we have in transistors. You can do it with mechanical elements as well. That's what he did. And in binary, by the way, he already used binary encoding system. So quite remarkable. He did draw up the designs for all of this, but didn't build all of it. He didn't have enough funding. But the scholarly opinion nowadays is that when you look at his designs, it would have worked if he just had enough funding and enough resources to do it. And then there was this woman called Ada Lovelace, who just through letter exchange with Charles Babbage knew about his design of a computer and developed a first algorithm on top of it. So also making history there. Then we have a big gap, I would say, until the era of the Second World War, roughly, when Turing, with the help of a Polish cryptographer Martin Rejewski, they built this machine called Bomb, which was able to break the German Enigma cipher. And this was kind of laying down the groundwork for also creating then an electronic computer that became also programmable. I mean, the Brits had one, the so-called Colossus. The Americans were building ENIAC to do kind of the same. It was also for breaking codes. And actually kind of unknown almost in history is this German guy called Konrad Zuse, who even before the Brits and the Americans already had a programmable computer that Zuse set free. But yeah, he's often forgotten about. And then we have in the center here John von Neumann, who became really the central figure in the US to bring computing to the world, and the whole industry in the US basically started building around these designs that von Neumann introduced. One critical innovation that I would say goes really back to von Neumann is the ability of the computer to not just be programmable, but for the program to be at the same place with data in the memory, so that the program could actually create itself. It's not even that much used, but for example, if you use a debugger, and the debugger is able to emit, traps inside of the program code so that it would break in there. That's something that was not possible before von Neumann's innovation. And actually that innovation was also quite central to what I'm going to talk about later with Douglas C. Engelbart. And then you have, for example, the Algol 58 committee with various figures here. You have Grace Hopper, whose work led to COBOL. And then based on this algol work, we have pretty much most of our modern programming languages are coming from that family, basically. So it all grew out of here somewhere. Now, you know, Engelbart himself, so not talking about the main figure in this talk, Douglas C. Engelbart, he was, I would say, a junior engineer on one of the successor computers built from like ENIAC pioneers at Berkeley. It was called the Chaldic computer. And during that time, he learned all about, you know, what is the classic computer architecture, how that, so he has that knowledge from that part of the tree branch. But there's actually a secondary branch that is maybe even less known, which is this branch down here. And if the upper branch is kind of digital computing history, then this is analog computing history, because that also existed going back quite a while. So you have, for example, Lord Kelvin also in the 19th century building this machine called you know, tight integrator, basically. So it was a kind of differential analyzer machine, all with analog elements. And then you have this character in the middle there. His name is Vannevar Bush, and he, without kind of, he did build it first without the knowledge of Lord Kelvin's work, but he basically made the equivalent of this mechanical device, but with electromechanical elements. But it was analog, so it was an electromechanical analog differential analyzer. He built that at MIT, and that was also one of these, you know, pioneer computing devices. He would also later found Raytheon Technologies, which, you know, is one of the biggest weapons manufacturers. And also, like, if we zoom into this influence now to Engelbart, he published an article that became quite influential. The article called "As We May Think," and kind of ironically, for someone who founded Raytheon, he actually argued that computers are not just this thing we should use for warfare, but to actually expand human mind and expand human capabilities. And Engelbart, that was even before his time at Berkeley, he was stationed in the Philippines as a radar technician. And, you know, he was isolated alone in this hut on stilts, in this traditional Philippine hut. And somehow he got this article from Vannevar Bush about, you know, how computers should expand our capabilities. And I imagine almost like a, you know, a monk kind of situation where something started turning in his head, you know, that's quite clear. So it was one of the major influences on him. And in the middle, we see here a device that Bush envisioned called the MEMEX, where basically for a whole, like the knowledge of one person is stored on microfilm, and it's indexed somehow, and you would able to tell the device through search words, you know, what part of the film it should spool up for you, and then display it on sort of this tablet interface. So it's really, it comes out of analog, you know, and a whole different way of thinking of you know, having a personal computing device in some sense, right? Not really a computing device, but like a knowledge retrieval device. And this also was one of the inspirations to Engelbart. So later, when Engelbart had his own research group, now at Stanford, it's called the Stanford Research Institute, he, you know, he still thought about these fundamental concepts. For example, what is intelligence? And for Engelbart, intelligence is really an elusively distributed, elusively distributed functional processes throughout a hierarchy. And it is depending on the organization of these processes. So to give you an example, he looks at the architecture at that time of computing, and the thinking is that only through the hierarchical organization of these different levels that they had, or we still have basically, intelligence can be created somehow, right? And this kind of neatly stacks up with these pioneers. You have basically the circuit architecture, the logic architecture. We basically kind of go from Babbage to Turing to von Neumann with the hardware unit architecture, how everything works together, memory versus ALUs and so on. And then you go into the higher levels in terms of software, at least with machine commands and lesser functions and so on. These would be kind of the first generation of programming languages. And then COBOL I would put as like more a higher level language than those represented here by Grace Hopper. So you kind of have these giants standing on each other's shoulders, and you are on top of it, and you can profit from this level of organization and intelligence to kind of propel yourself, right? And the way that Engelbart looked at this was, so if we want to augment our intelligence, then we need to kind of pull it apart into the different concepts. He talks here about artifacts, which are physical objects that the humans interact with. So, a keyboard and like a screen or something like that could be an example, but you could also just take a typewriter. Then you have language, which is, in his mind, kind of the modeling of the world with symbols and concepts. The methodology, which he puts as procedures to solve problems within that model that you built up. And then training, to basically take all of the above that you maybe have learned in school, and then you need to kind of start applying this in the real world to create some kind of value, for example, in business. And he puts that together in this drawing, where you have basically the human processes on one side and the artifact processes, as he calls them, on the other. They both have kind of interactions with the outside world. But then the big question is, what is the man-artifact interface? And to give you a little bit of context here, this is how IBM thought about this at the same time. So the article I showed you is from 1962. This is System 360, announced 64 by IBM and delivered between 65 and 78. Until 78, this was still delivered to customers in this way. And maybe you see something that is lacking here. What don't they have? They don't even have a monitor, right? They have a keyboard, they have a printer. Basically the human is there to kind of feed this big machine. The machine is kind of what's important about this. And you are just there to basically deliver information to feed to it. Reprogramming this is kind of thought as this major task, maybe undertaking, many engineering hours, probably distributed over a year or two. It's not really meant as like an interactive device that people could actually improve themselves. They just have to feed it, basically. And, for the Engelbart, this is just not good enough, basically. And his research group kind of started running with these ideas in their head, how can we actually improve on this interface between man and machine? And they started doing this experiment, basically. They took a group of researchers, 12 to be exact, to develop in an experimental laboratory an interactive computer display system, and also, you know, the whole interaction with the computer surrounding it. And the idea was to learn the principles by which interactive computer aids can augment their intellect, and to basically have a continuous improvement cycle where they improve the tools. This improves their capabilities again to improve the tools and so on. So they bootstrap the whole system from scratch. And they do have CRT workstations. So it's one of the earliest uses of actually having CRTs together with a computer. So the group was basically also the subject of the experiment, while also being the executor of the experiment, you know, kind of a unique setup. And here is what they came up with a couple of years later. This was for you.
So we're going to try our best to show you rather than tell you about this program. A very essential part of what we have developed technologically is what does come through this display to us. And I'm going to start out without telling you very much about the program and just run through a little bit of the action that this provides us. So in my office, I have a console like this, and there are 12 others that our computer supplies. And we try nowadays to do our daily work on here. So this characterizes the way I could sit here and look at a completely blank piece of paper. That's the way I start many projects. So with my system, that's a good start. I'll sit here and say, I'd like to load that in. So
the quality will improve. They have to kind of superimpose this image with image of the CRT. Right now it's showing.
So I'm putting in an entity called a statement, and that's full of other entities called words. And if I make some mistakes, I can back up a little bit. So I have a statement with some entities' words, and I can do some operations on these. I can copy a word, say that word like copy after itself. In fact, the pair of words I'd like to copy after itself, and I can just do this a few times and get a bit of material there. And there are other entities like text. Say after there, I'd like to copy from that entity point to that point, and it'll copy it. Great. So I could get myself some material on my blank piece of paper, and then I'd say, well, this is going to be more important than it looks. So I'd like to set up a file. So I tell the machine, all right, output to a file. And it says, well, I need a name. I'll give it a name. I'll say it's sample file.
A little bit familiar to VI.
And I'll say, please output it. It says it did. And then it comes back automatically with an origin statement or header telling me the name of the file and the date and the time and who established it. And thereafter, I can always do something. I can ask for the status of a file, and it'll tell me that information. Very small file now, owned by me, last written by me, very shortly ago, etc., and other interesting data in there. So we've seen how we can start with a blank piece of paper and go to developing a file. This file is one statement with a few words in it. Let's make more statements. I'll say copy that statement, and lo and behold, I have another one. Copy that one, another one. I can even copy groups of statements. I can say after that one, copy the group from there to there. And it does. I can look at that and say, probably goes off the screen. It'd be interesting if I could ask the computer to collapse that, perhaps to show me just the first line of each of those statements. All right, please do that. So it did. This is one aspect of what we'll use over and over again through this presentation.
How long did it take Microsoft to have collapsible text in MS Word? I wonder. Must have been until like 98 or so. But anyway, that gives you a little bit of a taste of what they were showing there. So these were their interfaces. They invented the mouse in this research group, something we all still use. And they went further than just the mouse. Actually, they were thinking, well, if you have one hand on the mouse, what is the other hand doing? Like this thing in the middle, this keyboard, that's actually made for two hands, right? So it's kind of annoying to switch from mouse to keyboard all the time. So instead, what they did was to have this 5-key piano keyboard on the left side, which was also capable of, with combinations, give you any letter, and then they would enter commands this way, so that you can do commands just sticking like the left hand on this piano thing, the right hand on the mouse, and then they operate together in a more smooth way. So they even thought further than kind of what we are now using, right? They thought this is kind of necessary. I mean, he goes on to show tree structures. So you can have, yeah, like trees in a file. You know, he goes from like markets or yeah, to cereals, and then under cereals in his shopping list he has like the different cereals to shop for. You have graphs, hyperlinked graphs actually. So now remember, imagine what IBM systems looked like at that time. It was typewriters basically and the printer. They had like graphs that were generated from their code structure and where you could click on one node and it would link into a file where you could look into a piece of documentation, for example. Like, this is not just 10 years ahead. This is 20, 30, 40 years ahead of their time, basically. So this system, you know, it's called NLS Computer System. By the way, it was 12 terminals connected to a mainframe. The whole mainframe had 64K. That's how much they had to work with. Their operations are defined using a DSL, a domain-specific language, for which they first invented a compiler, meaning, you know, a generator of DSLs that they can then use to define their problems in and then solve their problems, basically. And they build up this whole system by using these previously defined operations to improve the organization of the code, the coding itself, as well as its documentation. So if you look at the piece of program code that they have for any of these commands, they themselves are hyperlinked with other, you know, files in the system, so that you can, for example, jump from function definition to function definition, something that we need editor support for. They basically have it built into their whole operating model. It's also, you know, hyperlinked with documentation in this way, something we still kind of struggle with. And so humans and the system are kind of bootstrapping themselves together. Right, so I said it's a mainframe. Well, a mainframe is kind of...
I'd like to link to Bill, and I don't know what his terminal is right now, so I have to ask for somebody to connect me to him audibly. So, Bill, will you come in through this intercom?
Hello, Doug.
Hi. I need to know what terminal you're on, Bill.
13.
Okay. I'd like to have him see my text. And so this special thing, if I label 13, will switch over. So in his display, he sees my text. So I'll execute it. And sure enough, it does. But what's that running around? Well, if he's looking at my text, he'd like to have something to say about it. So we put on a marker, a tracking spot that he controls. So he's sitting in Menlo Park looking at this text, and he can point to it. But we've carefully reserved for me the right to control and operate on this. So my bug is more powerful than yours. But we can have an argument. Yeah. That's what they call a bug fight. So, all right. So in case you haven't been listening, Bill, we've been going through lots of examples and setting up in collaboration here so that we can go on into information retrieval. And we set up now audio coupling, and we're both looking at the same display, and that'd be very handy to work. We could talk to each other and point, and maybe later I could hand you the chalk on this blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available through the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I'd have to set up my display in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it. I can see your face, and we can talk. So let's do some collaborating. You're silent. Oh.
Okay. Well, they basically have MS Teams, right? With collaborative document editing. So, you know, this raises some questions here. This was 1968. Okay, that's what, 55, 56 years ago. You know, all these things they had, why don't we have some of them even? So for example, today, there's not really a significant editor that would use this mode where you can have commands like in VI that you can freely compose together and, you know, define yourself using macros if you want, and allowing the mouse as an input in these commands. It's always kind of, you know, this second-rate citizen, the mouse, when you use VI, I would say. Or why is MS Teams still just showing one additional mouse pointer? They could do that back then, like, why not 12? Why not everyone, right? So that you can point to something. Why is there no unified concept in POSIX, in the old POSIX standard that came, you know, almost a decade later than this system, for inter and inner file links? All we have is files, but they don't really link to each other. You need a whole bunch of software on top to be able to link between files. Why are we rarely using DSL generators like, you know, Lisp would be doing, for example? So from this work, oh, sorry, actually, to show this. From this work, a whole bunch of other ideas trickled through and grew into their own trees, you know. Alan Kay and other colleagues from Xerox PARC, they basically adopted Engelbart's vision. I mean, a couple of them were actually researchers coming from Engelbart's group. They then founded Xerox PARC together, and they built the first PC called the Xerox Alto. You know, they went the PC route rather than the mainframe route. Engelbart himself, he believed in the mainframe and didn't want to go into PC space, basically. You have this whole idea that already started with Bush, this you know, Memex thing that already defined hypertext. Actually, the idea of hypertext goes to back there. This inspired Tim Berners-Lee to create the internet, basically, HTTP protocol. You have people, you know, like, of course, Bill Gates and Steve Jobs, who then went to Xerox PARC and saw all these goodies and created our operating systems with it. Or you have someone like Niklaus Wirth, who created Pascal at ETH. And I want to leave you with this one quote I like from Alan Kay. By the way, very interesting figure as well. I recommend watching some talks of his. Best way to predict the future is to invent it. And seeing all that that Engelbart's group did, you know, we have to ask if you put this aside, what the industry was doing back then, you know, with the IBM 360, they were so much ahead. Like, what else are we missing today? Like, things that are kind of established knowledge, but no one, you know, thinks about combining it with some other, you know, tree of history, let's say, such as in that case, the analog computing world and their ideas. What combination of ideas would create something new today? Not just in computing, I mean, it could be in portfolio management, I think. So Engelbart, he bridged the ideas of digital and analog computing. And, you know, what are we going to bridge next? My question. So any questions from you?